In this video, we'll talk about logical equivalencies, kind of how to derive them, and we'll talk about one that's very powerful in particular. So let's start things off with kind of a big truth table. So as we've kind of talked about before, if we look at our original three here, if I satisfy H and I satisfy the conclusion, that would make H implies C true. If I don't satisfy H, or if I do satisfy H but I don't satisfy the conclusion, well, that would make the statement false. And if I don't satisfy the hypothesis in any way, but the conclusion is whatever the conclusion is, then it becomes vacuously true. And that's something we talked about in a previous video. So if I don't satisfy the hypothesis, but I do satisfy the conclusion, well, it's still true. It just doesn't really apply. And if I don't satisfy the hypothesis and I don't satisfy the conclusion, still, it's what we call vacuously true. Okay, so let's take a look at these other three columns. And it might seem a little weird, but just bear with me here. If I'm looking at not C, basically what that means is that's the opposite of our previous conclusion here. And I'm looking at, okay, if I did satisfy C, then there's no way I satisfied not C. So this would mean not C is not satisfied. It might seem a little weird, but if you think about it, they can't both be met at the same time. Similarly, if I look at not H, originally, I did satisfy it on this first line, so that means that I didn't satisfy not H. So that would mean this statement, not C implies not H, is vacuously true because technically not C is the hypothesis for my new statement. Now that might seem a little weird, but bear with me here. Okay, similarly, if I look at the line below it, the red line, if I do satisfy H, well then I didn't satisfy not H. If I didn't satisfy C, then I did satisfy not C. And this would make this new statement, not C implies not H, false. So I did satisfy the hypothesis of my new statement, which is not C, but I didn't meet the conclusion, which is not H. Next line down. So if I didn't satisfy H, that means I did satisfy not H. And if I look at C, I did satisfy C, which means I didn't satisfy not C, which again would make my new statement, vacuously true. I didn't meet the new hypothesis. And then if I look at not H, or if I look at H on my last line, that means I did satisfy H. And similarly, I didn't satisfy C, I did satisfy not C. That would make my statement true. Now, I'm not too worried if you don't understand the truth table just yet, but look at these two columns. For two statements to be logically equivalent, they have to be true or false at the exact same time. So if you look at these, if we just go right down, when H implies C is true, so is not C implies not H. And when it's false, they're false for the same, values of H and C for their hypothesis and their conclusion. So this would mean that H implies C is logically equivalent to not C implies not H. And that might seem a little weird. Now again, I'm not too big on knowing the truth table, but as long as you can take this result, this is a very powerful result in mathematics. Very important. This means that we can rewrite a statement, and it might be easier to prove this case than it would be to prove this case, or vice versa. So this would give me two options when I'm trying to prove something of how to prove it. So let's kind of put this to practice a little bit. Let's say we have a statement, if x equals 4, then x squared equals 16. And I think we could probably generally say this one is true. We believe this one for the moment. Okay, well, this would be logically equivalent to if x squared does not equal 16, then x does not equal 4. This would mean that these two can be used interchangeably in, say, a proof. Now, let's say I was given the second one I wrote in green. For starters, I was trying to prove this. That's very difficult to prove, very difficult to work with not equals. However, this one, much, much easier to prove if I wanted to prove it. So if I prove this one that I've circled in blue, then I've proven the one in green. That's where the benefit of this concept comes from. And this has a name. So if we look at not H, or not C, implies not H. This is called the contrapositive. And this is a very, very useful tool while you're writing proofs in mathematics. Now, a quick side note on this video, I want to talk about if and only if. So this is something that we see a lot in mathematics, and there's a couple abbreviations for it. We can see a double-sided implies arrow. It's a biconditional statement, or sometimes it's written as if with an extra F. So it's shorthand. Now, what this means is that if we have A, if and only if B, this is the same thing as A implies B and B also implies A. They go both ways, and it's something you see a lot with definitions. A triangle is a right triangle if and only if it has one right angle. We see it with all kinds of definitions. They're written like this. They have this phrase in them, and this is what this phrase means. It means that if I have a triangle with a right angle, then it's a right triangle. If I have a right triangle, then I know it has a right angle. It goes both ways. So it's very powerful to know this logical equivalency. Sometimes when we're trying to prove a statement like this, well, we actually have to write two proofs. We have to prove the one way, and then we have to prove it the other way. So it's just a note worth noting while we're talking about logical equivalencies. This is a very common one that pops up. It's just worth talking about.